All right, good morning, everybody. In case you're not aware, there are no classes on Monday, October 2nd, so that I guess staff, faculty, and students can participate in the National Day for Truth and Reconciliation. It's actually on Saturday, but the university has decided to cancel classes on Monday. And again, once again, you do have a quiz next Wednesday in class. You can read the announcements for details on the quiz. And I'm just going to pick up from the, I'm going to start with the next lecture from the next set of slides on cue. All right, so today's lecture is largely about recursion, using lists. Right, everything I talk about here, you can do the same, you can do recursion on arrays as well, but doing so on lists is a little bit easier because there's a special method in the list that array list has that makes doing certain types of recursive problems easier. And I'll explain that as when we get to that method. Okay, so to start, I want to start with the world's least exciting game. It's called Jump It. It's called Jump It. It's basically, that looks like an array or a list, right? So it's just a board that consists of a single line of squares. Right, so you have 2 or more squares. You always start on the leftmost square. Right, so the starting point is here, right? And if you look at the number in the square, that is the cost of how much, that is the cost of standing on that square, right? So starting on the first square costs you 0. You stand on the second square, that costs you 3. If you stand on the third square, that costs you 80, and so on, and so on, and so on. So the rules of the game are, you start on the leftmost square, and then you are allowed to take 1 step to the right. So I can go to the 3. Or I can take 2 steps to the right. I can go to the 80. The goal is to reach the last square, minimizing your cost, minimizing the total cost. Right? So if I start at the 0, I go to the 80, and then the 6. Right? So that's 80 plus 6 is 86, and then the 10, that costs me 96. Right? I would like to get to the 10 with the lowest cost. Your costs are always positive in this case. Okay, so the solution for this example here is the following, right? You move 1 square, that costs you 3. You move 2 squares, that costs you 6. And then you move 2 more squares, that costs you 10, right? So it looks like if we back this up, right? Your choice is between the 3 and the 80, so you choose the 3, right? And then it looks like what the decision is, well, I can go to the 80 or the 6, so I'm going to go to the 6 because that's lower. And I can go to the 57 or the 10, so I'm going to go to the 10 because that's lower. Or you can argue, well, the 10 is the last square, so I might as well just go to that square. Right, so it looks like you can solve this with what's called a greedy algorithm. Right? At each step, choose, at each step, your choice becomes that which minimizes it. Your choice is pick the next square that has the lowest cost. Right? So it looks, we call that a greedy type algorithm. Right, and so the question is can you always solve this problem with a greedy algorithm? The answer turns out to be no. Right? So picking the next square with the lowest cost doesn't always work, right? Because it turns out that it might be better to move to a square with a higher cost because you would have ended up on that square anyway. Right? So if this is the end of my board, right, and I'm on the 17, right, then if you choose the square with the next lowest cost, right, that's between the 1 and the 5, you're going to go to the 1. Then if you're at the 1, you're going to pick between the 5 and the 6, so you're going to go to the 5, right? And then if you're at the 5, you're going to go to the 6 or the 1, so you're going to go to the 1, right? So pick the square at the next lowest cost. But, right, it turns out you can save at least 1, right, by skipping that square there, right? So at the 17, forget about going to the 1, go to the 5 instead, right? And that costs you 1 lower, right? And these squares don't have to be at the end, right? They could be somewhere in the middle of the board. Okay, so to solve this problem, I want to solve this problem recursively. The reason I want to solve this recursively is because there is no obvious iterative answer to solve this problem. Right? So in other words, there's no obvious way to write a little loop that solves this problem. Right? The problem is because you, to write a loop, to write a regular for loop, you need to know how many steps you're going to take. And you don't know how many steps are in the minimum cost. Right? So that rules out the for loop. You could try to writing this as a while loop or a do while loop or something like that. But again, if you try to do so, it's not obvious what the logic is to figure out how to make to figure out how long should the loop run and what steps do you take in the loop body. And so turns out there's a very straightforward recursive solution to this problem. Right? So you all took recursion. They did do recursion in 121, right? Yes? Okay, good. So in any type of recursive problem, right, recursion is not natural for most people, right? So it's not really obvious how to form a recursive solution for most people. Some people think recursively, and so for them it's easy. But for most people, it's less obvious how this works. Right? And so there's lots of little pieces of advice that you can give to help you solve a recursive problem. Right? One of the things that usually works, though, is to try to sketch a small example of the problem. Right? If you sketch a small example of the problem, it shows you, hopefully it shows you the cases where you know what the answer is right away. Right? And remember, in recursion, when you find something where you know the answer right away, right, that's what's called a base case. Right? So typically, it's a small version of the problem. Right? Similarly, if you sketch a small example of the problem, that might help you figure out, well, how do I phrase the recursive part of the algorithm? Right? Okay, so let's try to sketch a small example of the problem. Right? So the rules of the game say that there's at least two squares. Right? So if there's two squares, you always start on the left-hand square. There's only one move, so you know what the answer is. Right? So if n equals 2, right, then you know just step to the next square. Right, so that's good. Similarly, if n equals 3, you also know what the answer is. Right? If n equals 3, you start here. There's no need to step on the middle square because the cost is never negative. Right? If the cost is negative, you might have to step on the middle square to reduce the cost. Right? But if there's 3 squares, you just jump to the last square. Right? So if n is 3, well, it's the same thing, right? You just jump to the last square. Right? And so it looks like there's a choice to be made if n equals 4. Right? So if n equals 4, we have a question mark. Right? So what do you do if n equals 4? Right? So I start here. Right? I might have to go here, and I might have to go here. Right? I don't know which one. Right? Either way, I end up at the last square. So that's the key, right? So if you're here, right? If you're in the case where n equals 4, right? You know that the next step has to reduce the problem to one of the base cases, right? Either I go to here, in which case you're in the n equals 3 base case, right? Or you take 2 steps, and now you're in the n equals 2 base case, right? So it looks like these are our base cases. Oh, what happened? All right. There we go. Right? So the board size is 2. Right? You have no choice for your move. You must move 1 square. So you know what the cost is. Right? If you're using a list to hold the board, right, then the cost of moving to the last square, that's the cost of being on the current square, right, plus the cost of the last square. Right? If the board size is 3, right, then it's the cost of the current square plus the cost of the last square, right? You don't step on the intermediate square. Okay, so you start to write your little recursive algorithm. So I'm going to represent the board as a list. I'm calling it list here. I guess I really should write array list here because we haven't talked about list yet. Right, so I'm going to change that to array list. I'm going to end up making the same change in every slide. Okay. All right, so typically in a recursive algorithm, your base cases are at the beginning of the method. Not always, right? It's possible to write a recursive method where the base cases are somewhere else. But usually they go often they go at the top, right, at the beginning. So if the size of the board is 2, I know what the cost is. It's just board get 0 plus board get 1. Right? If the size of the board is 3, then it's just board get 0 plus board get 2. Right? And there are your base cases. Okay, so what is the recursive case? Right? So if we go to the n equals 4 case here, right? So I'm here, right? I know the answer must be, right? It's either the cost of going 1 square, right? Or it's the cost of going 2 squares. And the cost is whatever is cheaper after going 1 or 2 squares. Right? So in other words, go 1 square, compute the cost of the rest of the board. Right? Go 2 squares, compute the cost of the rest of the board, right? And pick whichever is cheaper. Right? So compute the cost of moving 1 square, compute the cost of moving 2 squares. Right? And now the question is how do I compute the cost of moving 1 square? Right? The answer is you've got a method that computes the cost. Right? So that's the answer. Right? So this is where your recursive case comes in. Right? I just call the method again, passing in the appropriate board. Right? So in other words, if I start with this board here, and I want to compute the cost of moving 1 square, right, then what I want is the cost of that board there. Right? So if I can easily form this board here, I can just pass that board to the recursive method and let the recursive method figure out how much it costs to solve that board. Right? For the cost of 2 squares, I want the cost of this board. Right? So if there's an easy way for me to get that board, I can just pass that board to the recursive method and it will compute the cost for me. Right? And so there are your recursive steps. Right? And then you just return the smaller of the 2 costs. Okay, so how do I get the smaller board? Right? There's a method called sublist in list. So sublist is similar to but slightly different than a Python slice. Right? Sublist gives you back a sublist of the board. Right? Unlike in Python, though, unlike in Python, right, a slice is not a new list, right? So in Python, if you slice a list and modify the slice, the original list doesn't get changed. Right? In Java, if you modify the sublist, the original list gets changed. Similarly, if you modify the original list, the sublist gets changed. Right? So the method sublist, its indexes work the same way as a Python slice. Right? That's the starting index of the sublist in the original list. Right? That is 1 past the end index, in the 1 past the last element of your sublist, of the desired sublist. Right? So 1, start at the second element of the original list. Right? Go up to, but not including, index board.size. So go to board.size minus 1, right? Which is the end of the board. Right? So there's your list. Everywhere I'm saying list, you can just write oh, wait, you can't write array list, can you? Bear with me here. I just want to jump ahead. Oh, I'm going to have to jump ahead too far. All right. So this, oh, wait. Actually, I have to change everything. Sorry. Let me back up. There's a reason. Sorry about this. Where's my... I have to leave this as list. I'll explain why either this lecture or the next, but I have to leave it as list. And I'll explain to you what list is in just a second. Okay. So after taking 1 step, the remainder of the board, right, is the sublist starting at the next second element of the board, right? After taking 2 steps, right, the sublist starts at the third element of the board, right, and goes to the last element of the board. Right? The cost of your current square, right, is board get 0. So the total cost of solving the problem is the current square plus whatever is smaller after solving these two boards. Right? So the cost of solving that board is just the cost of taking one step. Right? I'm going to recursively call the method to compute the cost to solve that board. Right? The cost of taking two steps, I'm just going to use the recursively call the method, pass in the appropriate board, right? And math.min computes the min of those two values there. Right? So that gives you C, the cost of the current square, plus the smaller of the two costs of solving the rest of the board. Right? And that's your algorithm that solves this particular problem. Okay, so we've been talking about array list. And here I'm using list. And so I guess what's relevant for right now is that in Java, an array list is a type of list. Right? And so you can happily pass an array list to this method and it will work just fine. Right? Technically what list is what's called an interface. And I'm pretty sure I'm going to talk about that in the next lecture to explain to you exactly what's going on here. Right? But for now, wherever you see list, just imagine that it's array list. Right? The reason I can't use array list is because sublist returns a list and not an array list, unfortunately. And so that's why, and because I want to pass this thing to that method there, right? That also has to be list for now. Right? Next lecture, I'll explain what list, set, and map are. Okay, so if you've got lots of free time on your hands and you want to practice recursion, right? If you look at this method here, it tells you what the lowest cost is to solve a board. Right? It doesn't tell you what set of moves or what the sequence of moves is to solve the board. If you want to know the sequence of moves, that's a little bit harder. Right? So for example, to solve this board, I'd take one step, then two steps, then two steps. Right? It might be nice if you got back that information somehow. Right? So in other words, it might be nice if you could figure out that the sequence of moves was 1, 2, then 2. Right? And so you can modify that cost method, right? So that it takes in a board, right? It takes in, when you call it the first time, it takes in an empty list of moves, right? And then the method fills in the list of moves with the values 1, 2, and 2. Right? So if you like solving these little programming problems, right, you can try coding this up and see if you can get this to work. Okay, so that particular problem I just showed you, it has some quote-unquote nice properties. Right? So in other words, it makes it relatively easy to solve this problem. So number one, the rules of the game make it impossible to move to the same square twice. Right? So in other words, you cannot take a step of 0, and you can't go to the left. Right? Similarly, it's impossible to move off the board. Right? So in other words, because I can only take 1 or 2 steps, right, I never fall off either end of the board. Right? So if you change the problem up a little bit, then you end up with a much harder problem to solve. Okay, so it looks like a similar game. Right? So you've got a board. It's just represented as a list. Right? Each square has a number in it. Right? The number is not the cost anymore. Right? So you start at the left-hand side of the board. The goal is to get to the right-hand side of the board. Right? The number in the square represents the number of squares you can move left or right. Right? When you move, you're not allowed to fall off the board. So this says you can move 2 squares to the right. Right? It also says you can move 2 squares to the left, but if I try to move left, I fall off the board, so that's not a legal move. Right? 3 means I can move 3 squares to the right, or I can try to move 3 squares left, but that's not a legal move either. Right? And so on and so on and so forth. Okay, so to solve this board, when you start at the left-hand side, you only have one choice, right? You must move to the right. So we move 2 squares to the right. Right? Now I have to move 4 squares left or right. I can't go left, so I have to go right. Now I have a choice. Right? I can either go left or right. And so let's try going right. Right? So I go to the 6. Right? I can't move 6 squares to the right, so I must go left. Right? I can't move 3 squares to the left, so I must go right. Oh, sorry. right. Where am I? There. Okay. Now I'm at the 5. So it turns out I still can't move 5 squares to the left, but I can, in fact, go 5 squares to the right, and I have a solution. It's not the only solution. Right? So solution number 2, move 2 squares to the right, then 4 to the right, then 1 to the left. Right? I'm at the 2. Right? Now I can go left or right, so I can go there or there. Right? We already know from the previous example, if I go to the 6, there's a solution. But I can also go, I can also go to the left. Right? That takes me to the 2. Right? Now, if I'm on the 2, I can go back to the 2, right? But that doesn't really help us find a solution, right? I just end up going in circles, right? Or I can go to the 3. So I'm going to go to the 3, right? Then the 5, and then the 0, right? So it turns out there's multiple solutions. There's not just 2. There's actually more than 2 to solve this particular board, right? So in that example, I showed you that it's possible that you end up in what's called a cycle. Right? So add that 2 or this 2, right? That takes me to another 2, right? And so one of the choices is to keep on going around in circles, which I want to avoid because that doesn't actually lead us to a solution, right? So we want to try to, when we solve our problem, we want to avoid or find some way to avoid going around in circles, right? The cycle doesn't have to be of length 2 either, right? You might end up going to the 2 and then somewhere else which takes you back to the 2. Right, so that's also a cycle. Right? And because cycles exist, it's easy to make boards where there's no solution. Right? So this particular board is impossible to solve. So your algorithm needs to be able to detect, can it actually find a solution? Right? And on this board here, it doesn't matter what you do, right? You eventually end up on the 1. Oh, sorry. Right? So I eventually end up here no matter what choices you make. Right? So you end up at the 1. As soon as you end up at the 1, right, that puts you into a cycle. Right? You either end up back at the original square or you end up at this 2, and if you trace that out, you'll figure out very quickly you're stuck in a cycle. This board has no solution. Right? But it's not obvious looking at the board that there is no solution. And even without cycles, you can easily make a board where no solution exists. Right? So here I'm forced to move to the 100, and then by landing on the 100, there's no move that leaves me on the board. Right? Okay, so there's a couple of things here to keep in mind, right? We know that no solution exists, or the current solution is not feasible if you end up in a cycle, right? Or if you end up on a square, right, for which there are no more valid moves. Okay, so in every recursive problem, one of the hallmarks of a recursive problem is that every time you call the recursive method, the size of your problem gets smaller. Right? So in jump it, every time I move to a square, the rest of the board gets smaller. Right? If your recursive call leads to a larger problem, there's no guarantee that the recursion ever ends. Right? So you possibly end up in infinite recursion. All right, so in this game here, right, it doesn't look like the board gets smaller every time you make a move, right? Because you can go left or right, right? So it doesn't really look like the board is getting smaller every time, right? But it does, in fact, get smaller, right? So how does the board get smaller? Does anybody see why the board gets smaller every time? Every time you... Yeah?
You would never want to go back to the space you already were on.
Yeah, so you want to avoid cycles, right? So you never want to land on a square where you previously were. So the board, in fact, gets 1 square smaller every time you explore a solution, right? You never want to end up back on that square, right? And now we have another problem, right? So somehow you need to indicate to the algorithm that or to the method that you're writing, right, that I don't want to end up back on this square, right, where this square is the current square that you're on. Right? So I need some way to indicate that I've been on a square before. All right, so again, we're going to try to solve this with recursion. Right? Why? Because there's no obvious iterative solution. right? And I don't think you guys know any other ways to solve a problem yet, right? I think you know, try to solve it iteratively or with brute force, right? Or, sorry, iteratively, brute force is different, right? Or try to solve it with recursion. When you take your algorithms course, you'll learn a bunch of other different strategies for solving problems. Okay, so what are our recursive cases, right? So remember, so I'm solving this one backwards now, right? So instead of finding the base cases, I'm going to look at the recursive cases instead, right? So what are the recursive cases? Well, I know that if I'm on a square, right, and I can move left or right, so if the value in the square is small enough that I stay on the board, right, then I might want to consider moving left or right. So, can you move left without falling off the board? Right? If you can move left without falling off the board, right, then I want to know, okay, if I move left, can I solve the board? Right? So the method that I want to write is, right, can I solve a board? Right? So the method is solvable, attempts to solve that board, starting at that index on the board. Right? The first time you call the method, you'll pass in 0 for the index to indicate you're starting at the left-hand side of the board. Right? It returns true. If that board is solvable from that index, it returns false if the board is not solvable from that index. Right? So to answer the problem, can we solve the board by moving left? Well, I'm just going to call the method again recursively. Right? Okay, so that takes care of moving left, but you also have to take care of moving right. So if I can move right, then can I solve the board by moving right? Right? And so there are your two recursive calls, right there and right there. Right, so there's my method. Right? The base cases will eventually go here. Right? So I haven't worked out the base cases yet. I'll work them out next. Right? But for the recursive cases, right, I need to know how many steps to take. Right? So I'm on some square of the board. Right? I'm on this square of the board. Right? So I need to know how many squares left or right am I trying to move. Right? Well, that's just the value in this list at that index. Right? So the number of squares that I can move is just board get index. Right? And now I need some way to indicate that I don't want to come back to this square. Right? So what I'm going to do is I'm going to set the current value of the square to -1. Right? So I'm going to use a negative value to indicate that I've been on a square before. You could also use 0, I suppose, in this case. Right? Notice here, though, that the contract for the method says, right, the method does not modify the board. Really what it means is that the method does not permanently modify the board. Right? So I can change this list, right? But any change that I do to the list, I have to undo it. So temporarily set the current square to -1 to indicate that I don't want to come back to this square. Right? Can I move by going left? So that win left will be true if I win by going left. Right? So first of all, can I go left? Right? So I'm at that index of the list. Right? I need to move that many squares to the left. Right? So that's decreasing the index in a list. Right? So if index minus value, if that's a valid index, right? Now, or if it's greater than or equal to 0, right? Then I want to try to solve the board by moving left. Right? So when left becomes, call the method again recursively, right? Is the board solvable by moving left, right? Index minus value, that's the index of the new square that I'm going to go to the left, right? With that board, right? Remember that the board has been modified up here to indicate that I've been on the current square already. Right? When you recursively call the method, right, the recursive version of the method is going to set that index of the board to -1 to indicate you've tried stepping on that square before. Right? You want to do the same thing for moving right. Right? So, can I move going to the right? Right? Well, can I go to the right? right? So index plus value, that's the index of the square to the right, right, after taking value steps, right? Is that a valid index? Well, it has to be less than the size of the board, right? Okay, so if this is true, then I can move right. So I can try to solve the board by moving right. Right? After I've tried solving the board moving left and moving right, I have to remember to undo the change that I did to the board. Right? So I have to undo that step there, right? Which you can do by setting the current index of the board back to its original value. Right? I remember, right, so back here, I had the value, the original value of the square back here. Right? So I can set it back to its original value down here. Right? And now finally, do you win? Well, you win if either win left or win right is true. Right? And so there's the recursive part of the algorithm. Right? We still have to figure out what the base cases are. Okay, so what are our base cases? Right, so remember what a base case is in a recursive method, right? It's a case where you know what the answer is to the problem that you're trying to solve, right? For a method that returns true or false, there's probably almost certainly at least two base cases, right? There's one that corresponds to true, there's one that corresponds to false, right? So how do you know that the answer is false, right? If you hit a square whose value is -1, that indicates that you've been in a cycle, right? So there you know it's false, right? So the board is not solvable with this current solution, right? So you can abandon trying to explore the rest of the solution from that square and simply return false for that particular recursive case, right? When do you know you're done? Well, if you reach the last square, you know you're done, right? So if the current square is the last square of the board, you're done. You found a solution. Right? And those two base cases are sufficient to solve this problem. Right? Those are also easy to code up. Right? So is the current square that I'm on, is its value less than 0? Right? That means I've been on the square before, so return false. Right? Am I on the last square of the board? Well, the last square of the board has index equal to the size of the board -1. Right? If you are, you're done. Right? And then your recursive cases go here. Right? And so there's the recursive solution for this particular problem. Right? Notice that this version of the problem doesn't use sublist. Right? It sets an element, it modifies the list as it goes, and it undoes the changes every time the method is called. Okay, anybody have any questions about those two particular problems? All right. So let's look at a different problem. This one is more, I guess, more algorithmic. So it's something that's related to algorithms that you would have studied in CISC121. Okay, so I'd like to write a method that moves an element, the smallest element in the list, to the front of the list. You can write this method easily using a loop. Right? Use a loop, find the smallest element in the list, record its index, right? And then you can just swap the first element with the index of the smallest element, right? So you can do this easily, iteratively. You may have done this in one of your sorting algorithms, right? I instead want to try to solve this recursively. Okay. So here's my original list, right? It's the digits 0 through 9, all randomly shuffled, right? That's my original list. I want to solve this recursively. So in a recursive problem, you always try to reduce, in this case, the size of the list, right? So remember, I want to move the smallest element to the front of the list, right? Every step of the algorithm, I want to try to make the list at least one element smaller. So that's my original list. I'm going to say, well, look, I'm going to ignore the 8. Right? Instead, what I'm going to do is I'm going to look at the rest of the list. Right? So I want to look at the 7 all the way through to the 1. Right? And I want to say, well, look, if I can move, I want to move the smallest element in that sublist to the front. Right? I don't care how it does that. right? I just want to move the smallest element to the front, right? So the smallest element is the 0, right? So assuming that I can move the smallest element to the front, right, the 0 ends up here. I don't know what these values are, right? Because I don't know how the algorithm is moving the numbers, right? But I do know that eventually the 0 ends up here because it's the smallest element in the rest of the list, right? Okay, now you're almost done, right? So look, now I only have 2 values left in the original list that are important, right? There's the smallest value in the blue part of the list, and there's the 8, right? To move the smallest element now in the list to the front, I just have to look at these 2 values, right? So the 8's bigger than the 0, so I'm just going to switch them, and I get the 0 and the 8, right? And you're done, right? You've got the smallest element now at the front of the list. Right. The hard part in writing any recursive method is this step right here, right? Is this magic recursion step, because it looks unnatural. It doesn't look like this ought to work, right? But it does. Okay, so how do you do this? Well, it's not too hard, right? I want to write a method that moves the smallest element in the list T to the front of the list, right? So if you start to sketch out various problems of this type, right? You probably start out with, say, well, if you're clever, you start out with the empty list, right? So if I have the empty list, there's nothing to do. Oh, sorry. Right? So if T is empty, there's nothing to do, right? There is no smallest element. So I don't have to do anything, right? You might consider throwing an error, indicating an exception or something like that, right? But the most expedient thing to do is just to do nothing, right? If the list has 1 element in it, well, again, there's nothing to do. It is the smallest element in the list, right? And so it looks like our base case is simply, if the size of the list is less than 2, we're done, right? There's nothing to do, so you return, right? And now you just have to implement the picture, right? The recursive step says move the smallest element in the sublist, not including the first element of the list, to the front of the sublist. Right? So min to front takes in some list. Right? So all I have to do is figure out what is the sublist, right? And min to front will deal with moving the smallest element in that list to the front of that sublist. Right? So call min to front recursively, passing in the sublist that does not include the first element of the list. Right? Recursion happens, so something magical happens, right? And you end up with this picture here. Right? We don't know what happens here, right? But we know for sure that the 0 is going to end up here. Right? And now I just have to compare the first 2 elements of the list. Right? So this is a list of integer. So the first element of the list is an int or an integer. Right? So I just get element 0 from the list. Right? The second element is just t get 1. Right? Notice here that the base case protects you from these 2 methods throwing an exception. Right? The base case here says the list is at least size 2. So I know for sure t get 0 and t get 1 are both safe to do. Right? There must be a first element, there must be a second element. Right? If you're missing this base case, or if the base case is incorrect, one of these 2 methods will eventually throw an exception on you. Right? So get the first 2 elements of the list and then compare them. Right? If the second element is smaller than the first element, I just need to switch the first and second elements. Right? So if they are smaller, the first element becomes the second element, right? The second element becomes the first element, and you're done, right? If this condition is not true, then there's nothing to do. The smallest element in the list was always the first element anyway, right? So there's nothing after this if statement, and you're done. And so that, believe it or not, will recursively move the smallest element in a list to the front of the list. Right? Okay, now why am I showing you this? Right? Because you can use that method now to sort a list. Right? So what happens if I repeat that process? Right? Looking at smaller and smaller and smaller sublists of the original list. Right? So I call min to front on the original list, and I end up with a 0 at the front. Right? And now I call min to front again, this time on the rest of the list, right? So what does that do? That ends up moving the 1 to the front of the sublist, so I end up in this picture here, right? Now I call min to front on the rest of that list, right? So that moves the 2 to the front of the sublist, right? And I end up with 0, 1, 2, right? I now call min to front on the rest of the list, right? And so on, right? Until I get to this case here, right? Where the list is size 2, right? Remember what min to front does if the list is 2, so after calling this method here recursively, right? It moves the 8 to the front of the list, right? And then I end up with the 9. If I call min to front again, min to front does nothing because the smallest element is already at the front of the sublist of size 1. Right? That's selection sort, which hopefully they showed you in 121. Right? Selection sort says repeatedly move the smallest element in the rest of the list to the front of the current sublist. Right? That's all that selection sort does. Right? Hopefully they showed this to you. If they showed it to you, they almost certainly used a pair of nested loops. Right? Or you broke it into 2 methods. One that moves the smallest element to the front of the sublist, and then a second method that repeatedly calls selection sort. Right? You can do this recursively as well, though. Right? There's the recursive version of selection sort, assuming you already have min to front. Right? So if the size of the list is bigger than 1, right? Move the smallest element to the front of the list. Then sort the rest of the list. Right? So there's selection sort in 3 lines, assuming you already have min to front. Right? Now, min to front doesn't have to be recursive, right? It could be iterative, right? So that could be an iterative version of min to front, right? All it has to do is move the smallest element to the front of the list T, right? The recursive part is there, right? And also notice in this case, there doesn't appear to be a base case, but there is in fact a base case, right? So the base case here is if the size of the list is 1 or 0, right? Do nothing. Right? But you don't need that base case here, right? It only calls the recursive case if the size of the list is greater than 1, right? And away you go. So there is the recursive version of selection sorts. Right? Why does it work? It works, in part it works because of this magical method sublist, right? Sublist returns the part of the list corresponding to the specified sublist, right? If you modify the sublist, it also modifies the original list. I'm going to not do this slide, so I'm going to stop here. And I'm probably not going to discuss this. So this is, at some point in time, I don't know which course you do this in, you have to solve a recurrence relation. Right? If you want to figure out what the complexity of the recursive version of selection sort is, you can figure it out by solving a recurrence. Right? You solve that recurrence there. When you solve that recurrence, you end up in O(n) squared. Right? So selection sort has complexity in O(n) squared. I don't want to solve the recurrence here, right? Hopefully you know how to do this. If you don't know how to do this, come talk to me sometime during office hours and I'll show you how to do it, right? Okay, otherwise we're done. So the next time I see you is during the quiz, right? Sorry.
Monday and during the quiz.
No, there's no class on Monday. So the next time I see you is Wednesday, so that'll be your quiz day, right? Remember, there's no class on Monday. And that's university-wide. So if someone tries to make you go to class on Monday, they're not allowed.